Welcome everyone to our colloquium, and today we have the honor of host Amir Dembo from Stanford, and Amir will tell us about random graphs, statistical physics, and complexity.
Thank you very much. It's a pleasure to speak in the colloquium at the Boston University, and thank you, Ron, for inviting me. This talk let's start with the outline. So I will start with an introduction to a few areas which are not, two areas which are not actually mathematics. First, statistical physics, and then constraint satisfaction problems, which is a part of concerning computer science, theoretical computer science, and my introduction to both of these areas, as well as the rest of the outline. The survey and review of references will be extremely biased. I will only review the minimum things needed, and also my review of it will not be introduction to statistical physics, no introduction to constraint satisfaction problem, but just introduction to the minimal amount we need in order to carry out the theme of this lecture. And after that, I will talk a little bit about random graphs and average complexity, and that's already in mathematics. Then some results, prediction, and theorems for constraint satisfaction problem coming from statistical physics. And this is the first part of the talk, which will be more review part. And then I will move to another topic, also motivated by statistical physics, a short review of large deviations, which is a certain element of aspect of probability theory, and something called naive mean field approximation, which comes with statistical physics. And lastly, the relationship between these two topics and mixtures of products. And this will be the more technical part of the talk. If I will get there, if not, you will benefit by not having the technical part. So let me start with introduction to statistical physics. As I mentioned, a very biased introduction. I will start with the Gibbs measures or Boltzmann distributions. That here are Boltzmann and Gibbs, classical statistical physicists from the 19th century. And the Boltzmann distribution, which will be really the current theme for this lecture, is a distribution. It's probability measure, which in physics represents the behavior of molecules or some other particles at equilibrium in a microstate sigma. Sigma is your item, usually from a discrete. In our case, it will be from a discrete space, usually a large discrete space. It is of the exponential type. There is a weight which is exponential. In the weight, the exponent in the weight is the energy, or Hamiltonian, and it's multiplied by a coefficient which represents the inverse temperature. The higher the temperature, the smaller this term, and the closer you are to a uniform area. The lower the temperature, the more the energy is relevant. And there is a parameter n, which is the size, suggesting that the size of sigma involving n coordinates, and n is very large, and we will be interested in the behavior not of this measure, but actually of a system as a sequence of measures, as also called the thermodynamic limit. And the history of these measures, it starts with Bernoulli, which suggested that the heat of a gas is related to the kinetic energy of the motion, and the pressure is the impact of the molecules on the surface. Maxwell wrote the first statistical physics distribution, suggesting this type of distribution for molecular velocities. Boltzmann then formed the maximum entropy principle, saying that if you only observe certain observations and you don't know anything else about the measure, why don't you put a measure of this type, which has a maximum entropy, that is a maximum uncertainty, subject to what you observe. So you put your observable into the energy, fix it, and leave everything else undetermined. And this principle has now been guided principle in many areas in statistics and information theory, which have nothing to do with statistical physics. Gibbs wrote a book quite a few years after Boltzmann suggested this, and suggested that this approach, which Boltzmann suggested in the context of molecules of gas, actually carries over to statistical mechanics for mechanical systems which have no gases in them. And in particular, in mathematics, it's called Gibbsians. We call Gibbsian measures whenever we think about these measures also in the limit when n goes to infinity, which are not even really probability measures with these weights, but rather the asymptotic limits in the setting. And modern statistical physics went one step after Gibbs to suggest that one actually doesn't need to consider other mechanical systems in physics, but one can just remove the word physics from the whole thing and just use these measures to model whatever you want to do in other areas of science. And a prelude to that, I will talk a little bit about the work of Lenz, Ising, and Perls in the context of the Ising model as an example of a statistical physics system which has nothing to do necessarily with gas. And here is a situation. This is supposed to be a toy model to your refrigerator magnet, which holds nodes on the refrigerator door. And how is it done? It's done by putting a metal at low temperature in a situation which will create magnetism. And how do you do that? The electron spin has two possible states, which create, whether it's spin one way or another, it creates a magnetic field for this particular atom, which can be going up or down. And if you align all of them nicely in the up direction or in the down direction, doesn't matter, then you create a magnetic effect. If they are mixed up completely, you are non-magnetic. And the Ising model is a toy model which represents this by using some kind of a toy Boltzmann distribution for this phenomena, ignoring all sorts of secondary effects. And you're talking about a lattice. This is a picture taken, simulation taken from the internet of the Ising model in 2 dimensions. The spins are plus or minus ones, and you have temperature, high temperature. You have this picture. Here is high temperature. The red and the green represents a particular spin. You see they're all mixed up. At very low temperature, you either get most of them green in this case, or you can get some simulation, most of them red. So it's not perfect, but it's very close to this picture. And it's interesting thing happened at critical temperature or critical beta, where you have kind of patches of both the plus and the minus coexisting in a complicated and interesting manner. We will not study this anyway, so let's move on. So here is a mathematical model for the Ising model. So you have a graph. You don't need to have a lattice. You can take any graph you want for that purpose. The Ising spins takes the value plus and minus 1, and they're sitting on the vertices of the graph. And here is the energy. The energy is just the sum of the inner product of the two spins over neighboring spins. The edges represent who is neighboring of who. In the lattice, you understand, it's just a box and the nearest neighbor spins. And what is the energy trying to do? What the energy is trying to do, it's minimal when all the inner products are 1. That is either all of them are plus or all of them are minus. And if it's mixed up, it's going to be close to 0. They will cancel each other and not give us any benefit. We can have a ferromagnet, which is what I talked about as a magnetic element when beta is positive. So you try to make them all align. You can also have the opposite. We'll come back to it later in this lecture, the antiferromagnet, where you're actually trying to make them conflicting. Now, the antiferromagnetic will be much more complicated to study because if there are odd loops, you will not be able to do that because you will try to do -1, 1, -1, conflict. If you want all of them to be the same, it's very simple. Just make them all the same. Very good. Now, Lenz invented this model as a toy model with a Boltzmann-Gibbs measure with this Hamiltonian as a toy model to the magnetism. The story I just gave you. Assigned it to his student Ising as a PhD. Ising looked for phase transition. He could analyze very nicely the case where the graph is one-dimensional because there are very few connections. Found out that there are no phase transitions. Wrote a paper where he speculated the same no phase transition also in dimension greater or equal to 2. There was nothing really spectacular about this work, so he kind of left the field. And then 11 years later, Perlis showed that actually when you move to 2 dimensions, and this is also the case in any other dimension than 1 dimension, you now have a much bigger boundary, and you do have the phase transition, just like the simulation I showed you. Now, in 1925, obviously people could not do these simulations, and therefore there was no evidence that Ising is wrong until Perlis proved the opposite. And after that, there have been many works by Onsager and many other people on the Ising model in various cases and shapes and forms. We will not get to it. Now, here is a situation showing us a graph with, but not an Ising model, but a disordered model. In a disordered model, what happened in the Ising model, as I mentioned, you either all the weights have plus beta, or all of them have minus beta. So either all of them want to be the same or want to be the opposite. In a disordered system, you can have edges where you try to be aligned and other edges where you try to be non-aligned. Okay? And these choices of edges will be done randomly. And this is an example of a toy model for a glass. Before we did a toy model for a metal disordered system, toy model for a glass. A glass is a solid, but it's a non-crystalline solid. It's a solid that actually, if you leave alone for a few hundred years, will melt. If you look at all the glasses, you will see that they are moving down. And what you have here, a spin glass is of course not a glass, but it's a toy model for glass model, and it's really a disordered magnet. What is a disordered magnet as a toy model? It means we take exactly the same Hamiltonian before, but we put in front of our product sigma I, sigma j, a weight for every edge, ji, j, which is also plus or minus 1. And to make things simple, because it's quite complicated, we don't know how they're distributed, we just choose a jij randomly. So we just flip a coin and choose whether it's plus or minus 1. And often we will even do it symmetrically, so the pluses and the minuses have symmetry, meaning we choose a jij to be plus 1, probability 1/2, and minus 1, probability 1/2. Now, this is an example of a family of toy models for spin glass. And the first model proposed was by Edwards-Anderson model in 1975. And this was for when the graph was Z2. They proposed it, but nobody knew what to do with it. Nobody knew how to analyze it. And I think even up to today, people, even in physics, don't know. Or there is no consensus of a formula for the Edwards-Anderson model. So Sherrington and Kirkpatrick, shortly thereafter, suggested, why do we do Z2? Let's take the complete graph. Everything, we have n vertices, everything is in the edges, must be simplified a lot. They simplified it a lot and solved it incorrectly and wrote it in a paper in physics. That's one of the examples of an incorrect solution, like the Ising model. Incorrect solutions in physics are quite rare, but they're usually very insightful. So there was an incorrect solution. And then Parisi, there was after that, quite a lot of papers in the late 70s and early 80s trying to correct the solution. It became very clear, very quickly, that the solution was incorrect because it didn't make sense. And Parisi predicted a structure, and in particular, this structure predicted a Parisi formula for the Sherrington-Kirkpatrick model. And Parisi afterwards, many years later, got the Nobel Prize essentially for this contribution. Because this contribution came to be quite insightful to solve a lot of models in statistical physics, not just this one. After that, 20 years later, there was a Viana-Bray model, which corresponds to the same problem, but now instead of a complete graph, a sparse graph. Sparse, let's say, random graph. For example, Erdos-Renyi graph we will meet with edge probability, which is constant over n. Essentially, a graph where the number of edges does not grow like the number of vertices squared, but at a much lower rate. So not everything is present. And in that case, the Parisi formula will not apply, and it's not so clear what will apply, but there are some conjectures. Okay. Moving out of statistical physics. Introduction to statistical physics is over. And now introduction to computational complexity and constraint satisfaction. Now we are shifting gear to a different area, which will be related eventually, but a priori it seems to be completely unrelated. And this is a classical problem in computational complexity of P versus NP. So what is the story here? We have a decision problem, a formal question of yes or no answer, depending on an input of varying length n. So it's a family really of questions. You give me a Boolean input of n zeros and 1, and the family of all 2 to the possibilities have an answer either yes or no, and you are supposed to characterize a yes and a no, essentially to run some machine and tell me what the answer to this input is. So, for example, an answer, either an assignment of Boolean variables for which a given Boolean, I give you a Boolean formula, which is represented by an input of size n, it tells you what the formula is, and I ask you, is there an assignment of the variables for which the formula is satisfied? And this is called the SAT problem. And it's an example called constraint satisfaction problem, because in the formula there are some constraints. You have to do certain things to be satisfied, and you need to do all of them. Now, a decision problem is in a class P if there is an algorithm that answers correctly whether you are yes or no at a polynomial in the length of the input number of steps, which means that it effectively can be run on a computer at reasonable speed for moderate or not, or even large, but not extremely large size n. If it is in a class NP, if we already have a polynomial algorithm for checking whether an answer is correct, but we are not sure whether we have a polynomial algorithm for actually figuring out whether there is. It's easier, it's often very easy to check if a proposed answer is correct or not than to find if there exists such a correct assignment. And Stephen Cook in 1971 proved that there is a particular problem called 3-SAT, that if 3-SAT has a polynomial algorithm, then every problem that can be checked quickly also will have a polynomial algorithm. So he reduced the question. So he said, look, if you can find a good algorithm for this one, then there will be a good algorithm for many, many more problems. So reduce the whole problem into one problem. And since then, there have been many reductions. These problems of this type are called NP-complete. And the $1 million prize by the Clays Institution is to resolve whether P is equal to NP or P is not equal to NP. Most mathematicians believe this, but there is no proof. On the other hand, if you can do that, you will revolutionize computer science, because many problems which are considered hard will suddenly become quite easy. And there are many constraint satisfaction problems in the family of NP-complete of this type. I already mentioned 3-SAT, but also independent set and max-cut and 3-coloring. And in this talk, I will tell you what these two problems, independent set and max-cut, are, because those are easier to relate to statistical physics, which is my goal. Okay, so here I will tell you what is an independent set problem. So this is a constraint satisfaction problem. You give me a graph, but the graph can, of course, be represented by a collection of zeros and ones for which edges are in and which edges are not, of size n choose 2. And here is an example of the graph. And the question is there a set of vertices of size k with no edges in this set? There are edges, but no edges between the vertices in this set. Sorry?
Anti-click. Anti-click.
Anti-click. Yes, anti-click. And I marked here the size of the largest independent set. If I did not make a mistake, they are marked in purple. And you can see that there are edges out of them, but no edges between two perfect vertices. So in this case, you have an independent set of at least size 7 in this particular zone. And the constraint satisfaction problem is to answer this question for large K and large N and given the given graph. Or to answer the question, what is the max size of the maximal independent set, which is really a Here is how you make it into a problem in statistical physics. It is called the hard-form model. Your vertices are now, instead of being using spin, they are 0, 1, but that's really the same. And you put this Boltzmann distribution. It has a weight, which is a number of ones, but it also has these factors in front, 1 minus sigma I, sigma j. There is a product here, but you can, of course, write it as an exponential by putting it in a log and adding it to the coefficient. Now, this encodes independent set, because the independent sets are the sets of indices where sigma I is 1. Because there cannot be, if there are two ones neighboring, you get a factor here which is 0, which will kill the whole product. So this is your constraint, and this is your weight. You have also in Gibbs measure, or in Boltzmann measure, you always have a normalizing constant, which I failed to mention before. The normalizing constant is intended to make them into probability measure. So just really a sum over all the configurations of this weight. Now here you can see that only independent sets will give you a factor 1 here. And so what you get here, Z beta, is just a sum over all possible choices of independent set of e to the beta, the size of S. If you take beta equals 0, you simply count the number of independent sets in the graph G, which is also interesting. If you look at the limit 1 over beta log z beta, which is also called in statistical physics the ground state energy, because it gives you really the maximum value you can get to this Hamiltonian, or minimum if you put Hamiltonian in statistical physics with a minus. And this ground state energy will give you the size of the largest independent set in the graph. So finding for all graphs the solution to this problem is NP complete, so probably hard to do. Here is another constraint satisfaction problem, which is also related to another problem in another model in statistical physics, which I already mentioned, the antiferromagnetic easing, and is a max cut problem. In the max cut problem, it's again a problem on graphs. You have a graph, here is a graph, and on the vertices of the graph, you assign weights 1 and -1. And once you assign weights 1 and -1, it defines a cut. Are all the edges connecting between S and the complement of S. And every cut has a size, which is the number of edges in the cut. So in this particular example, the red cut has a size 2, 1, 2. So what is a cut? Really is a number of edges between S to the complement of S. And you can, max cut is a maximum of all cuts over subsets of the graph B. But what you can do, you can take, if you calculate, you can see that if you take twice the size of the cut minus the size of E, you get exactly H of sigma for an easing on G, which takes a value +1 and -1. That's exactly your configuration. So in particular, 2 max cut minus the size of E is a ground state energy for the antiferromagnetic easing. So if you can solve the problem of finding the ground state for the antiferromagnetic easing, you can solve the max cut problem. Because the number of edges is something you know. That doesn't resolve it. So it's another NP complete problem related to statistical.
What's the definition of ground state?
It's a 1 over beta log of z beta limit as beta goes to 0. Or if you want, it's a minimum or maximum of the Hamiltonian overall configuration. Minimum, maximum, depending whether you put it somewhere or not. The way I did it here, it's probably a maximum. Maybe minimum. I don't know.
Yeah.
With minuses are clear.
We are interested in exact solution, not in bound.
Sorry?
We are interested in exact solution for
Yes,
statistical mechanics
right.
application.
You're interested in?
Let's say, when you ask this in graph theory, sometimes you cannot solve it, but you can give good bounds.
Right, right.
Are there relevant
We will get
in
to
the statistical mechanics?
We will get to it in a minute. So actually, this problem, as we know, these problems are very difficult. We already know. I mean, if they were not difficult, P was equal to NP. We don't know that yet. Okay, so what can we do? We can ask the question, are these problems really hard? What does really hard mean? Really hard means we already know that there is some graph, there is some instance, some long instance, which will take us a long time, presumably, to solve. But maybe on many graphs, maybe on most graphs, are quite easy. Just there are a few esoteric graphs which cause problems. So we really want to know something about constraint satisfaction problem on the average, or if you want, typically. But to define typically in these two examples, we need to define a typical graph. So now we come to the question, what is a typical graph for these trends? And this brings us to the next topic, which is random graph. And will get us back to statistical mechanics. I didn't have problem. So average complexity involves random sparse graphs. So we need to define a model for random sparse graph. And there are two most common models. One is the Erdos-Renyi random graph from 1959. What do? It's called G and M. You have n vertices and m edges. You can tune the parameters. You are usually looking at n very large. You can tune the relation between m and n to see how sparse or dense you want to do. Of course, if you take n choose 2, you have the complete graph. If you take n equals 0, you have the empty graph, and somewhere in between you can have dense and sparse graphs. And what you're doing is saying, okay, I gave you the number of edges, I gave you the number of vertices, and I don't want to give any other constraint. So I will just take a uniform graph among all the graph with this specified number of edges. I don't want to specify anything else. And you can easily check that the average degree of a vertex is 2m divided by n. every edge connects to two vertices, and then the two edges, divide by n, that's the average. You can take a more restricted model, which is called the random regular graph, where I denoted by G regular, in which case, again, n vertices, but now, instead of only specifying the average degree, we want to specify that the degree of every vertex is exactly the same parameter gamma I took from above, and then I'm uniform among all the graphs with the number n and the number gamma. The only constraint that you can see about these two numbers, obviously you want n times gamma to be even, or else there will be an empty set, because the total number of n's of edges must be even. And what are sparse graphs? Sparse graphs correspond in this context to gamma, which is order 1. That is a number of edges proportional to the number of vertices. In our context of statistical constraint satisfaction problem, every edge represents a constraint. You want to have it not in the cut, or you want to have it independent, or whatever, and every vertex represents a degree of freedom. So by choosing edges proportional to vertices, you're kind of on the border between being able to satisfy it and not being able to. If you go more, it will always be impossible to satisfy. And now we want the program is to study constraint satisfaction problems for graphs taken from either one of these models, and seeing whether for large n, we can say something about, for example, what is the value of gamma for which typically we can satisfy the problem, or we cannot satisfy it. Maybe later about algorithms to do that. And this will be average complexity theory in this context. And this is also where statistical physics enter combined with computer science. Now, to do that, we need to understand how large random graph look like. And the claim is that large random graph looks like a tree. In what sense? Locally. So here is a simulation of a large random regular graph with the degree 3. Let's see, everything here has degree 3, hopefully. It's not my picture, but I, of course, borrowed from one of my students, but it's correct. And you choose a vertex at random here, like that one. And then you look at the neighborhood and you see, the neighborhood is like a tree with 3 children. You continue, it's still a tree. If you continue more, at some point it will stop being a tree, but hopefully it will take a long time to demonstrate. I will not do that. Yes. So
logarithmic time.
Logarithmic time. But logarithmic is large. It's not constant. Meaning growing. If the size of the graph grows, here, again, what do I mean by local convergence? I mean, fix a distance. If you make the graph large enough, at this distance, the neighborhood would look like a tree for almost all the vertices. It's a very weak notion of being near a tree, but it's good enough for the purpose we want. And also, it's only one clean enough that we will have. If we ask it to be a tree, it's not a tree. Not going to be. Okay, so the claim is, or observation, is this notion which I told you up verbally, a regular graph, uniform regular graph with n gamma will converge to the regular tree T gamma in the sense of neighborhood of size k when n goes to infinity and k stays fixed. And Hans Bethe, which is who is again a statistical physicist, but a more modern one, contributed a lot of things to statistical physics. Among them was physics predictions. He did not work on constraint satisfaction problem, but he worked on problems in statistical physics, which converge to where the graph is sparse enough to look like a tree locally and make a prediction how the result for Gibbs measures on such graphs will look like. And detailed predictions by Hans Bethe can be transformed into average complexity theory. That has been done, and then they can be you can try to prove this conjecture. So here is the first conjecture, and the first conjecture is that there are linear number of equations that determine the local marginals in the large system limit. Now, if you have a system of size n, the measure involves 2 to the n configuration, so it will be very difficult even to write the marginal. But the claim is that there is a way to write much smaller number of equations, which if you solve them, you get approximately the one-dimensional or even finite-dimensional marginals of your system. And here is the situation. Again, I re-express my Boltzmann distribution, not as an exponential, but as a product, like a constraint. And then comes the beta-Pearl's equations. These are really three recursions. I want to calculate the marginal law of the value of my configuration at point I in a graph to which I excluded one edge. I took my original graph and I cut out one edge from I to j. Now I have a part of my graph and I want to know what is going to be the marginal of my measure if I just remove the connection ij. And the claim is that this you can more or less, approximately at least, write as a recursive equation. You give me the value you already know of such things from L to I, then I can do a small calculation involving only degree or finitely many things, not growing with them, and get myself the new margin. And if you want, you can just write equal here and try to solve it simultaneously. And you have here the number of equations you have here is like the number of edges. Since we are talking about number of edges growing like n, these are nonlinear equations, but you can solve them somehow. And these objects are called sets of messages. And the idea is, where is the idea coming from? This is a tree recursion. The idea is the following. If E would have been a tree, then once you disconnect the edge from I to j, the whole part connecting to I will be completely disconnected from the whole part connecting to j. And therefore, you can calculate the marginal for each I. For each I, you can calculate the marginal for it by looking at the contribution from every one of its children, because if you disconnect them, they will also be disconnected. So you get yourself an exact identity. It's very easy to check that if the graph was a tree, you have an identity. Now the claim is the graph looks locally like a tree, why not this holding approximately? This prediction might be right or might be wrong. It's only a conjecture or a heuristic. And this is called messages because they're kind of telling I a message coming from J. What do I say about your value? Right? And then you combine the messages and get the messages to send from I to J and go on and go on. And this algorithm, or an algorithm behind, you can also think of an iterative algorithm where you put here iterating n, iteration n plus 1, write equality, and try to solve for a fixture. And this kind of algorithm is called belief propagation because it kind of propagates your belief from here to there. And this is an algorithm which is often employed in statistics and AI to solve various problems, sometimes with justification coming from statistical physics and mathematics, sometimes simply because it works without any justification. And the philosophy, again, is to approximate local marginal of our measures in terms of measures on trees. Because of the previous slide, the sparse graphs look like this. This is one prediction. A second prediction, which is really also related to that, is that one of the things you can do, imagine you have a tree-like graph sequence now, sequence going to n. You can write your normalizing constant, which is the sum of the product of the psi's, and imagine that these psi's are taking just a value 1 and 0. Psi is 1, representing a constraint being satisfied, psi equals 0, representing a constraint unsatisfied, and therefore the whole thing is gone. In this case, the sum here is just telling you how many solutions you have to this constraint satisfaction problem. So you can look at the asymptotic growth of the number of constraint satisfaction solutions. This is also called free energy density in statistical physics, which is a limit 1 over n log Cn. You expect, since sigma has size 2 to the n or constant to the n, you expect Cn to either be 0 or grow exponentially fast. And this will tell you what the exponent is. And this exponent, especially if you put here all sorts of parameters, also carries information on the qualitative behavior of large problem instances which are satisfied. So the ones which are not satisfied, it doesn't tell us. And here comes the beta prediction. The beta prediction is, it says the following. Imagine a situation that you converge to a tree in the notion we mentioned, and beta claims that this number will be a function that depends only on your tree. It doesn't depend on your graphs at all, just on their limit. And it can be calculated as an explicit functional of a set of messages. You take a Gibbs measure on the tree, for which you can calculate everything by this recursion principle I told you, slightly different recursion principle. And it has a beta-Pearl structure, meaning I take a Gibbs measure where the law of every marginal, think of this as a finite subgraph of your tree. the law of this finite subgraph, is a law that you get by just looking at these psi's inside the subgraph, and the effect of the outside, you take a product of functions only of sigma I, only of the guy coming from outside, exactly like in this belief propagation. So imagine that this graph is part of it, not only of a tree, but the boundary condition is a product. This is called the beta Gibbs measure with entrance law H star. And what H star do you choose? Beta even tell you what H star to choose. They said, H star must be a fixed point of the belief propagation updating curve. Doesn't tell you which fixed point to choose, but tells you already to do it. So this is a particular conjecture, which may or may not hold for constraint satisfaction problem, but if it holds, it can tell you also what parameters this problem will be solved or not, because if the problem has a solution, typically the phi will be positive. If it doesn't have a solution, the phi will be minus infinity. So this end will just be zero. And the nature, the ergodic theory of probability is such that if there is a lot of independence here in the graph, you expect this limit to be non-random, and according to beta, just depend on the limiting tree and not even on your sequence. This is called the replica symmetric solution because it corresponds to a situation where everything looks the same. An easy picture is replica symmetry breaking, obviously much harder. We will not get to it at this moment. There is another prediction related, this is more vague, but another prediction which applies to independent set and K-sub, the two problems I mentioned, also to max-sub, is that the hardness of the problem is related to the set of possible solutions splitting into lumps. What does it mean? You look at the parameter alpha represent here the number of constraints per degree of freedom. In independent set, it's a fraction of occupied vertex. Every occupied vertex causes some constraint because it doesn't allow other people to be occupied. And in a K-sub problem, it represents the number of constraints or clauses related to the number of variables. And what happened, as you increase this number, in the beginning, the set of possible, of course, it's not a set of possible solutions, not a Euclidean ball, but you can think of it vaguely as Euclidean ball. That means what? That near each solution, not far from each, you will find another solution. Or if you want, you can, in principle, with local moves, somehow explore the set of all solutions, cleverly. Then comes a point called the dynamical phase transition, or alpha t, at which point the problem suddenly breaks down. You get exponentially many blobs, each one of exponentially, but smaller size, and they are differing by a difference, maybe even up to n from each other. So you actually need to make a global move in order to move from one to another. Then there is another set phase transition called condensation phase transition, where all these exponentially many things collapse. You have one guy which takes, let's say, half of the solution. The second guy takes a third of the solution. The next guy takes a fourth of the solution, and so on and so forth. And all together they carry all the solutions. Then comes another phase transition, which is the one maybe of most or only interest in computer science, where there are no more solutions. And using statistical physics, statistical physicists were able to actually, for independent set, K-sub, max-cut, all of these problems, numerically find these numbers in the limit n goes back. Get a formula like that, using a method called the replica symmetry calculation, replica symmetry breaking calculation, which we don't know how to do rigorously, but they give people in computer science and people in probability motivation to write theorems where they justify explanation. Hence the connection between these three fields. So here are some mathematical results coming from probability theory in connection to this whole story. So first, this is following a conjecture of Zdebova, Zdeborova, and Bocher from 2010 in the statistical physics literature. This is a paper I wrote with Andrea Montanari and Subodh Vatasen. And what we proved, we take both Erdos-Renyi graph or regular graph, and we look at the size of the max cut in such a graph divided by n. The leading term is trivial. The leading term is simply the number of edges divided by half. y, take a typical cut. You will get half of the edges will be a plus and minus 1 on the other side, and the other half will be equal. So you can get gamma over 4 easily without any work. There was an interest in computer science in finding the next factor, which was of a square root of gamma. You can imagine the degree gamma being large here, otherwise there is no content to this theorem. But n goes to infinity and gamma stays large but fixed, maybe 10 to the 6, fixed. And then in computer science, starting with the work of Bolovash and Malone from 1990, different methods were used to provide lower and upper bound on the coefficient in front of the square root of gamma over 4. In 2013, Bayati, Gamarnik, and Tatali proved that the limit converged to something using subadditivity methods. But subadditivity, as we all know, usually doesn't tell you anything about the limit, so it doesn't help getting the limit. And in this paper in 2017, we proved that the coefficient in front of the square root of gamma is actually the ground state of the Parisi formula for the Sherrington-Kirkpatrick model on the complete graph. And this object was a work of intensive interest in probability theory, starting with the work of Guerra and Toninelli in 2002, and Talagan in 2006 in a very celebrated work, built on the work of Guerra and Toninelli to show that the Parisi formula is actually correct, because there was some debate in the statistical physics literature whether Parisi prediction is even correct or not. There were alternative formulas proposed, and Talagan proved that all the formulas that people were debating in statistical physics were all the same. Hence, no debate needed, because if A equal to B, you don't need to worry whether it's A or B. The debate was between two formulas, and they proved to be correct, which was very surprising because a priori they don't look at all this. Anyway, the surprising fact here is the appearance of a number coming from statistical physics in the max cut problem, and in particular a number coming from spin-glass, because I mentioned to you the max cut problem is a problem on antiferromagnetic model. But antiferromagnetic model on random graph will behave as a spin-glass if the degree is large. This is what we proved. And this came, I think, as a part of a surprise to people in computer science, because the connection, except for the work of Dembo and Bocher in the physics literature, in computer science, there was no realization that this constraint satisfaction problem has something to do with the SK model. Hence, people did not even look for this as the answer. They just wrote numerical bounds from above and below by using first, second, higher moment method, and those things will never reach the P star because there is no explicit formula for P star, which is given in this way. But once you prove that the models are the same, you don't even need to compute it. You just rely on parameter. Another paper on a different problem, actually much harder work, by Ding, Sly, and Sun in 2016. It's part of a collection of works, and they proved that if you look at the fraction of vertices occupied by an independent set, there is a threshold alpha S, which is the maximum fraction of vertices you can get occupied by an independent set, or the size of the maximum independent set in a random regular graph. This is restricted to regular graphs. If you take Herber-Schreini, it's much more complicated. In principle, there is a prediction, not in principle, the prediction. In principle, the proof that Ding, Sly, and Sun do will work there, except the paper is already 100 plus pages, and it's guaranteed to be 10 times more if you try to do the same method for a more complicated method. So probably one needs to first find a way to do it much simpler before attacking the other problem. And this number, the sharp threshold alpha S, come from another prediction in statistical physics, which is also interesting, called the 1RSP, or one replica symmetry breaking. It suggests, again, a limiting Gibbs measure of a local structure, which is a Gibbs measure on a graph. The difference is that now, instead of putting here H star, some fixed numbers, some fixed probability measure over the sigma takes 0, 0, and 1. So H star is just a probability for getting a 0 and probability for getting a 1. But in this small model, the number here is itself a random number. So looking at a given neighborhood, you will find the boundary, you will have to put random numbers. And how do you choose a random numbers? The random numbers are chosen according to a law. And this law is a fixed point of a belief propagation update, but not in the space of numbers, but in the space of laws on interest. So you elevate yourself to one level up and then do the same problem. And you can think now, understand what's happening if you have two RSB. You just elevate it. Now, it's getting more and more hairy if you try to write the equations, but the equations for one RSB are actually not so bad because this guy is a probability measure on 0 and 1, so it's just a number between 0 and 1. So this Q star is just a law on 0, 1, just a probability measure on 0, not so bad. Afterwards, come a probability measure on probability measure on probability measure, probability, getting hairy even to say that. And the beta RS prediction is a prediction for counting. And if you want to relate this whole story to how it relates to the original problem, remember that near alpha S, I expect to have solution clusters. So what I can do, I can write another problem where instead of counting solutions, I try to count clusters. If I write some approximate Hamiltonian for counting clusters, I arrive at a problem which is easier. I can apply to it the beta prediction, and therefore it's a fixed point of this. But I need to go to a different level in order to do that, because the cluster will be represented by law. Okay, so this ends the first part of the talk. And now I shift gear to another part of the talk, which will be short, about large deviations and naive mean field approximation. There is no more connection to computer science, connection maybe to statistics or to other problems in science, but it's also characterized by, here it's characterized by a topic in probability, which is quite classical, and a new take on it coming from a motivation coming from statistical physics, but in a different situation. So first I give you a short crash course on large deviations. What is large deviations? We consider probability measures, sequence of probability measure on a common probability space, say metric space, but you can think about it 0, 1, x. And the large deviation principle has two parameters, some function and some sequence Rn that goes to infinity typically. And it says that the log of the probability of a set should be like your minus a constant times Rn. So this really represents a decay, an exponential decay of the log of the probabilities in question. Large deviation is not about things of constant probability, but things of probability going to 0, and you don't really care. Probability is very small, only on the rough way in which they go to 0. The scale and the constant in front. And the claim in large deviation principle is that you can write the coefficient in front of your rate as a solution of a variational problem. Every point in space will have a number, and you just take the smallest. Smallest number correspond to largest probability because it's of the minus which appears. And the question you can ask yourself now, if you are a mathematician, what set E can you take? And what is this double wiggle? Rigorous formulation was given by Baradan in 1966, analogous to convergence in law for probability measures, meaning he says the following: takes the log in the left, divide by Rn, takes the limit, and the limit will be below this number if the set will be above this number if the set is open, and below this number if the set is closed. So you get an upper and lower bounds, depending on whether your set is open and closed. If your set is nice enough that the upper bound with a closure match the lower bound with an interior, you are done. You get yourself a limit. And the reason for this type of formulation, same as the reason for convergence in law, this formulation is weaker than pointwise convergence, but infinitely better because you will have infinitely many examples where this will work and convergence pointwise will not. So it's a necessary evil. And the intuition is that if you want intuition for this whole thing, but without open and closed sets, is that the measure you have has a density which looks like that, e to the minus j times Rn plus something small. For large n at every point x, imagine you have this density, then clearly if you take the log, take the 1 over n, you will get this point. Convergence even pointwise and even for point. But if you don't have exactly a density, you still have a good result for that. Now you can see that if you choose a finer in this business, I mentioned the space, but I also mentioned a metric, and you see that the finer metric is a stronger statement because you have more open and closed sets. In a weaker metric, you will have less of them, and you will have weaker bounds. In particular, if you have a large deviation principle, then whenever you apply a continuous map, you automatically get another one, because you just make your metric, if you want, weaker when it's continuous. Now, the large deviation principle, this is a mathematical fact, it requires a measure to strongly concentrate on compactness. It's difficult or almost impossible to do it unless your measure charges most of the mass on compact sets. And this is called in a technical term exponential tightness. It's easier to have it if you have a coarse metric. And if you make your metric too fine, it's just impossible to get a statement. Maybe it's just wrong. Of course, it's difficult to prove an impossible statement. Now, in examples, it's often not even clear what to do because it's not even clear what to put as a common space. And the good example I have in mind is mu(n) is the law of a random graph of n vertices, but per n I change the space, so not clear what is a common space here. By now, there is a rich theory around large deviation principles, especially for weighted averages of independent variables, or if you know probability, nice Markov chains or Gaussian processes, but there are quite a few examples which is not covered by the journal. And here is an example which is covered by the general theorem. Actually, the most classical example. If you are attentive, you will notice that this is a theorem by Sanov, predating even the theorem of Varadan. It was achieved before the formulation was done. Here you are looking at the probability distribution of the empirical measures, the fraction of letters that you have of every symbol. You think of the space of symbols as being just finite space. For us, maybe like Ising spins, plus and minus ones. This is just a fraction of ones and the fraction of minus one in a sequence of independent, identical distributed random variables with a certain law for every variable. And Sanov proved that this will satisfy a large deviation principle. The rate of decay is n, you have n degrees of freedom, and the function here is going to be the relative entropy. And the relative entropy for discrete space is very simple. It's a sum of the probability in one measure times the log ratio or the log likelihood between the two measures. Now, a key identity which will be relevant for our purpose, and it involves Gibbs measures, it involves really measures of this type, exponential weight times the probability measure in front. This is a normalization constant in a Gibbs measure. Exactly, I just wrote integral, but you can think of it as a sum. And what it says is that the key identity for this is a formula for the log partition function. You can write this log of the integral as this optimization problem. And checking it is very simple. Try to solve this optimization problem and write Euler-Lagrange constraint. Look what the optimal is, get the answer. It's really a one-line calculation. And this appears in the proof as a key identity in the proof of Sanov's theorem. Kramer proved another theorem, even before Sanov, for the large deviation principle for tails of averages of random variables. This is a more involved object, involved empirical measure. This just involves the empirical average. This is exactly the object that plays a role in the law of large numbers. Law of large numbers says this will converge to the expected value. Central limit here will tell you the fluctuation of this object. Large deviation tells you the rate of decay of this object. And in particular for us, yi here will be some functional in Rd. Think of it as a deterministic function, bounded functional of this xi, and you can see that Kramer's theorem is a special case of Sanov's theorem, of course proved almost 20 years earlier, by contraction, by applying a continuous mapping from delta x to g of x. And we will denote mu and g, the law of Sn, later on in the next 2 or 3 slides. Mu and g are the law of these measures for this particular choice yi, which is g, and the distribution of these objects satisfies the large deviation principle with an explicit rate function. How do you prove that? The way you prove this theorem of Kramer, the way Kramer proved this theorem, you find a coefficient beta, so that if you will take this law and do this operation, changing it by putting in the exponent beta times g, the typical value will move and become x. And then you just calculate, use Radon-Nikodym theorem for the Radon-Nikodym derivative and approximate the Radon-Nikodym derivative for large n, show that it concentrates, put it outside of expectation, and you will find the value of J. And this is a method that will appear later in a more modern. And here is a situation we are interested now, is something also motivated by statistical physics. Now we take a sequence of Bernoulli variables, 0 or 1, like in the constraint satisfaction problem, with a parameter P which might depend on N, and a number D which also might depend on N. So D will grow with N, P might go down with N if we want sparse values. And we are interested in a smooth function of Boolean function, if you want, or non-Boolean function, non-negative function of the configuration space. And let's suppose that we already know that the tail probabilities of this function decay at a rate exponential to the minus Rn. And what we are trying to do is to figure out what's the coefficient in front of Rn, which is really like a large relation to exponent. But we don't know how to put them in the same space. We have no idea how to collapse them. So what do? We can consider Gibbs measures on Yn given this way. We just put some function h of the configuration, this function h of the configuration, and look at this new measure mu and h. And it has a partition function associated with it, given by that. Now we can use a relative entropy. We can write relative entropy also for product measures or for general measures of n symbols. And we have this key identity. The log of the partition function can be written as a supremum over all possible measures of this function. I just copied the key identity from before, but decorated everybody with n to demonstrate I'm working on spaces of increasing size. What is a naive mean field approximation? This approximation, this identity doesn't really help me. Solving this problem or approximating this value is difficult because I need to sum over exponentially many discrete configurations. Here it looks better because I'm doing a variational problem over probability measurement. These are probability measures over exponentially many configurations. So I didn't really gain much. I didn't really gain actually anything. But if I can restrict this space to a smaller space, I might be in better shape. The naive mean field approximation says, why don't we assume, or maybe we can prove, that this original supremum is approximately, that is a leading term. I know that this number should behave like order Rn. Maybe the leading term in front of Rn is obtained by doing the optimization only over product measure. Remember, the measure here, mu(n), is a product measure. So maybe even though I put this general H, maybe the optimal solution inherits the product somehow, or at least can be approximated by the product. So I can do this, and I can call psi n of h this variation. Now, this variation is much better to do, because what I can do, I can replace the discrete variables by all possible 0, 1 to the variables. I can write for each one of them Rn h of q minus Ipn. This is just a relative entropy that corresponding to replacing this Bernoulli with Bernoullis with numbers qx. And you sum them up and you write it inside. Now, this is now a continuous optimization problem. Maybe you can use differential calculus, and there are really only n parameters, q1 up to qdn, dn parameters. So you can maybe optimize for each one of them. And this problem, I can assure you, is much easier to solve than the original. Now, of course, it leaves the question, when is this naive mean field approximation holding? Now, what is the connection to large deviations? The connection to statistical physics I already mentioned, the Gibbs measure. Connection to large deviation, you want to calculate an indicator, you want to check what's the probability of fx, some function of x, which of interest to you greater or equal to n. What you can do, you can make a smooth approximation of this indicator by a function e to the h multiplied by Rn, where R is very large. So this is going to be, you think of h as being 0 when f exceeds n, and being minus infinity when f is less than L, then it's exactly the indicator, but this is not a continuous function. So I smooth out this 0 infinity, and I get the log of this Zn is going to be a good approximation to, on the one hand, what interest quantity I'm interested in, and on the other hand, it's going to be given by this formula by just writing this variation. So if I can solve this formula analytically, or divide by Rn, find the leading term of this formula, then I got myself the leading term in the large deviation principle, but without doing a large deviation. I did not go to a common space. I didn't know how to do it. I kind of bypassed the whole thing. Okay, this brings you to the question, conditions for this to work. And in a paper with Shurov Chatterjee, we found out that here is a good condition, which actually is satisfied by many examples, is that you have this condition if your function, either f or h, has a low complexity gradient. What is a low complexity gradient? You calculate, first of all, the function originally is in the discrete space, but you can define derivatives either by going from one point to another or by interpolating the function inside and then defining the Euclidean derivative, so you can calculate a gradient. Now, if you go over a size 0, 1 to the dn, something with dn bits, and calculate a function, you will typically need order dn bits to approximate the collection of numbers in there. Low complexity gradient means that you can actually approximate the set of vectors you get quite well by a net of much smaller size. Instead of exponential in order of dn, it's exponential much smaller than the Rn that you want to get in the end. And if you do that, then we prove, that's what the theory of this paper proved, that if you have this condition, then you can show that the log of the n is approximately up to smaller little order of Rn, the variational problem I promised you before, the main field approximation. And from that it follows that the minus log of the tail will be approximated by this other variation. Now, if you have an application in mind, you still need to do two things after the general theory. One, you need to verify that you have the low complexity gradient condition. And secondly, if you really want a nice answer, you need to look at this new variational problem that you got and solve it and check that in the limit, divide by Rn and send n to infinity, you get a much nicer version with an explicit quotient. If not, you are stuck with something which still depends on n to take it. And the proof of the general theorem goes along these lines more or less. You divide two cells of this partition, and at each cell you approximate the original Gibbs measure that appeared in this problem by another nicer Gibbs measure with depending only linearly on your argument. And for those, you can easily do large deviations, provided you restrict it to n. So it kind of tells you that the Gibbs measure under this condition is represented by a mixture of not too many product measures. I will come to it in a minute. Now, we had a success in a paper with Nick Cook, following quite a few papers that I wrote with Nick Cook on this topic. We can do this very well for subgraph count in sparse random graph. So this is a model where you take a sparse random graph like Erdo-Schreni, and you try to calculate what's the chance that it will have, let's say, a number of triangles, which is not the typical number. And it goes down exponentially, and you're trying to calculate the leading order of the exponent. And this was a commonly open problem in extremal graph theory that was solved by this means. You did this naive mean field approximation, you justify this. Some other people, Bhattacharya, Ganguly, Lubetsky, and Zhao solved this variational problem, did the second part of this. Ron and Eldan, in a paper that followed our paper by 2 years, extended the whole theory to Gaussian setting, where you are not working on discrete space, but in a Gaussian space, and got much better conditions, and on and on and on. There is a lot of literature I'm not going to spell out. Now, the low complexity gradient really means that this measure, Gibbsian measure, is well approximated by a mixture of product measures. And this was done by Eldan and Gross, Renan Gross in 2018. And Tim Austin in 2018 made another proof, which is very insight, I think very beautiful, very short, and allowed even for growing the alphabet because he needed it for dynamical systems. And what he did, he essentially says, assume that you have a partition, not too large cells, which induces on H a low complexity gradient. Then the Gibbs measure, he claims, is well approximated by a mixture of not too many product measures which are based on the cells of P. That means that you can write the Gibbs measure, these are the weights it gives to the cells of P, and the relative entropy to some product measure, to some nice product measure, will be very small on the average. And the nice thing about this proof, and this will be the end, the nice thing about this proof, the proof is solely by using information identities and inequalities. You don't need the whole story I gave you before. It goes to a different direction and gets to this conclusion. So it's interesting in the sense that you see different fields of mathematics interacting in this slightly more technical example. And as before, the first part of the lecture was about different fields of science. And let me just summarize the lecture. Constraint satisfaction problem of much interest have physics representation or statistical physics representation. Average complexity involves studying random sparse graph. There are detailed statistical physics predictions. There are mathematical proofs for some of them. There are many which are not proofs, so lots of more work if you want. Naive mean field approximation is a new tool for a class of challenging large deviation problems. I may add, coming also from statistical physics. Low complexity gradient related to having mixtures of products is an approximation to your measure, and also to naive mean field approximation. And the whole thing is connected because it's all related to Gibbsian measure going back 200 years, almost 50 years. Thank you.
Thank you very much. Quick questions, comments?
These low complexity gradients, and I guess this is not something that would generally happen for, I mean, it depends on the function for which you need to find.
Right. So low complexity gradient does not happen for disordered systems. This is why statistical physicists call it naive mean field approximation, because they think of mean field approximation what beta did, which is much more complicated. However, naive mean field approximation works, for example, for subgraph counts, because they are all, especially if you try to make some pattern appearing more than once, they are kind of ferromagnetic. They are trying all to go in one direction, but they also apply for arithmetic progression of given size in a large random set, counting those things, which is different discrete problem. They have proved to be useful for doing the Potts model on hypercube. So they do apply in quite a few challenging problems, but they don't apply in many other problems. The guiding principle is that the second part of the lecture will never apply to the first part. Meaning, if you're doing problem coming from challenging complexity theory, typically it will mean that there is no good understanding of good configurations, meaning that there is probably disorder or some conflicting or frustration in the system. Products will be broken. But if you don't have that, then it's still challenging, you can try the same.
Other question? Okay, let's take a